All right, we'll begin today. So let's get settled in. I do have an announcement about another pre-veterinary society meeting this week. There's going to be a neurologist coming, so if you're interested in that, whether you're part of the organization or not, that's going to be happening on Thursday at 6 p.m. All right, so then the other thing before we start, I've been getting some questions about looking over the exam from last week and regrades and stuff, and that's all fine. Just so we're perfectly clear on this, if you want to request, any points on your exam, if you think something was graded harshly or incorrectly and want to, when we take a look at it, I'm happy to do that. Make sure it's by the end of the day, Friday. You can either come see me in person, or as long as you send me an email that's dated sometime on Friday, I'll look at it for you. I don't want to get in the situation like I was last semester when we didn't have this clear wording on the syllabus and people were coming to me after the final exam and saying, oh, well, hey, what about this exam question? Can you give me points for that? So as long as I hear from you this week, that's fine. And I can still review the results with you anytime after that, but if you want to actually get points back or have me look at that possibility, that needs to happen this week. So with that, we'll just get into what we've been doing, which is in Chapter 5, we're starting to talk more about measuring quantities of chemical substances and this concept of the moles. And we're gonna continue on that today and now start talking about chemical compounds. So when we introduced it, we saw it in the context of single elements. And now we're going to see it in the context of chemical compounds when we start talking about molar mass and molecular formula today. All right, so we introduced the atomic mass last time and said that one interpretation of atomic mass, the one that's most important for us, is that it's the mass in grams of 1 mole of that element. And we have an exactly identical or exactly analogous quantity for chemical compounds. And so it's stated more generally as molar mass, and as the name implies, it's the mass of 1 mole of a compound. And really the same idea applies to elements as well. If we have the molar mass, it's the mass of 1 mole. And so because of that, the units are going to be grams per mole. So molar mass has a lot of synonyms or pseudonyms, I guess you want to call them that. Other ways that we can call it, but they all really mean the same thing. So sometimes you'll see it referred to as molecular weight or molecular mass sometimes. The formula weight or mass. And those are probably the ones you'll actually see. So depending, if it's technically speaking, if it's a molecular compound, you could use the terminology molecular weight. If it's an ionic compound, formula weight is probably more appropriate, but they will often be used interchangeably, so don't let that confuse you. They all mean the same thing. There are some abbreviations for this that you should be aware of as well. So there's one that the old textbook used to use, which may be phased out of the homework assignments by now, but in case you see it, it's just a script M, so it's a big cursive M basically. And then also you'll see MW, which would be, again, molecular weight if you wanted to see how that correlates. So those are the two abbreviations we'll use for it, but again, the units are grams per mole, so when we give those quantities to you, it should be fairly obvious what we're referring to. And then the way that we calculate this for a compound is quite simple. So we saw that last time. From the periodic table, we can get the atomic mass for any element, and that's the mass in grams of 1 mole of that element. And if we want to do this for a compound, we just have to add together the individual atomic masses. So we have to know the chemical formula. So we take the chemical formula, we add up the individual atomic masses, and that's going to give us the molar mass for that compound. Okay? So that's how we calculate it, and we're going to see a bunch of examples today, and then also not only how to calculate, but then how to use it in doing certain conversions and certain other types of problems. So let's start with a fairly simple example. We have the amino acid glycine, simplest amino acid, has the chemical formula C2H5NO2. And we want to know, what is the molar mass of glycine, which has this given formula. So the key thing to keep in mind here when we're, as I said, when we want to calculate the molar mass, we just need to add up the individual atomic masses. But be aware of what these subscripts tell you. They tell you that that's how many of, the relative portion of each of those elements in the compound. So if we want to find the mass of 1 mole of C2H5NO2, we have to be aware of what this chemical formula tells us, which is that because there's a subscript 2 by the carbon, that means we have 2 moles of carbon. The subscript of 5 on hydrogen tells us there's 5 moles of hydrogen in 1 mole of this compound. And nitrogen doesn't have a subscript, so that means there's 1 mole of nitrogen. And then we have 2 moles of oxygen for every mole of glycine. So if we want to find the molar mass of glycine, we have to keep in mind that there are this many moles of carbon, hydrogen, nitrogen, and oxygen in there. So of course when we add up the atomic masses, we have to account for that. So if we're going to start summing them up to get the molar mass, we have the atomic mass of carbon, but we have to then multiply it by 2 because there are 2 moles of carbon. So if we go to the periodic table, we can find the atomic mass of carbon. Remember, that's the number that's below the symbol. So the atomic mass of carbon is 12.01, but there are 2 moles of carbon in that compound, so we have to count for it twice. So we take 2 times 12.01. That's the contribution from carbon. We have to then take the contribution from hydrogen, so there are 5 moles of hydrogen. And the atomic mass of an individual hydrogen atom, again, comes from the periodic table. And that's the first one, 1.008. So that's what we get from hydrogen. 1 mole of nitrogen, so we just have to use its atomic mass once. Nitrogen is number 7 here, and the atomic mass, which is what we need, is 14.01. You'll start to, whether you try to or not, start to memorize a bunch of these that you use all the time. So nitrogen is 14.01. And then finally we have 2 oxygens, and the atomic mass of oxygen is 16 if we find it in the periodic table. So when we add all those up, we get 75.07 grams per mole. All right, so the mass of 1 mole of glycine is 75.07 grams, and that's the sum of all the individual atomic masses, accounting for how many of each of them there are in the formula, which we get from the subscripts. All right, so don't forget the part there that we have to include the subscripts when we add up the atomic masses. All right, and then one more example that is just a little bit more difficult. Determine the formula mass of lead. Sorry, what do you guys have in your notes? Is it iron or lead? Okay, so I didn't change it. Whoops. All right, I meant to change it. All right, lead 4 sulfate. Okay, so we have lead 4. I should have given you the formula, the abbreviation for that. That's not one you have to remember, but that's Pb. So remember that the 4 tells us that the charge on the cation is +4. Sulfate is SO4 2-. So if we want to balance the charges, the correct formula for lead 4 sulfate is going to be lead with 2 sulfates, SO4 taken twice. Okay? So that's the formula for lead 4 sulfate. So the things we taught you before about nomenclature will still come up occasionally. So that's the formula. Now we can get the formula mass, or the molar mass, by adding up the individual atomic masses. And because it's an ionic compound, formula mass is more appropriate than molecular mass, but we calculate it the exact same way. So we have have 1 lead in the formula. So if you look at our chemical formula here, 1 lead, and we have to find Pb on the periodic table. It's pretty far down there. Number 82 here, mass of 207.20. So that's the mass of lead. All right, and then here's where we have to be a little bit careful with these ionic formulas. So remember that when we have a something in parentheses, SO4 with a 2 on the outside, that means we have 2 complete SO4 2- anions. So that means we have 2 sulfurs. So remember that this subscript 2 on the outside of the parentheses applies to both the sulfur and the oxygen. So we have 2 sulfurs because there's 2 sulfates total. And the atomic mass of sulfur is 32.07. And then for oxygen, we have each sulfate has 4, but there are 2 sulfates, so 2 times 4 is 8. So whenever you have subscripts with subscripts, then on the outside, you have to multiply those 2 together. So 4 oxygens for each sulfate, 2 sulfates total. That's going to give us 8 oxygens in total. All right, so make sure we add those up correctly when we're doing this. So we have 8 oxygens. And because I have the wrong notes here, I'm not going to know what the answer is until I look at this in a second. Get my calculator out. Maybe someone could yell it out if they're faster than me. But 399.32, somewhere there. All right, thank you. All right, I had meant to change this to something else and I didn't. So, all right, so that should be what you get for lead sulfate. All right, so again, just the slightly different thing here is when you have polyatomic ions, you have to make sure you account for the entire thing. So SO4 taken twice means we have 2 sulfurs, 8 oxygens. That's really the only difference there. All right, so that's how we calculate formula mass, and that's fairly simple to do. And then on some problems, we'll just give you the formula mass. We won't expect you to calculate it, but you do need to be able to do that. Now let's look at how we can use the molar mass or the formula mass in certain types of conversions and certain types of problems. So this is very much almost identical to what we did last time with elements. Now we're just going to do it for a compound. So this is a real compound that one of my students made in my research lab, and it gives off red light. So when you hold up a black light to it, it glows red. It's just pretty fun. And it, as you might have guessed, it's an iridium compound. That's my favorite element. And the compound has a molar mass of 774.94, and we want to know how many molecules of this compound are in a 1.00 gram sample. So last time we saw how we could figure out the number of atoms in a sample, sort of in a 2-step conversion going from mass to moles and then moles into number of atoms. We can do the exact same thing for molecular compounds, but keep in mind that for a molecule, for a compound, because it's made up of molecules, the molar quantity that's going to be relevant is the number of molecules in there. So we do the conversion exactly the same way. We're looking for the number of molecules, and I'll just abbreviate this as iridium with brackets. It has a very complicated formula, so I'm not going to give it to you. But we want to know the number of molecules in here. So again, we're given the mass and we're given the molar mass. We don't have a direct conversion to go from mass to number of molecules. We can use moles as an intermediary. So if we take the mass and first convert it to moles, we have 1 gram of the compound. And we can, again, we want to convert into moles, and we want the grams to cancel out. All right, so since grams is in the denominator, that's where we put the molar mass. So it's 77.94 grams per 1 mole. We want the grams to cancel, so we put it in the bottom. So that gets us into moles of our compound. But now we want to know how many molecules there are. This will give us moles, but remember 1 mole is 6.022 times 10 to the 23rd of whatever entity makes it up. So if we want to find the number of molecules, we want the moles to cancel. And so we have to use Avogadro's number in the numerator. So there's 6.022 times 10 to the 23rd molecules per 1 mole. Last time we did it in the context of elements, so there's that many atoms per 1 mole, but if it's a compound, there's going to be that many molecules per mole. And so when you multiply this out, assuming I did my math right, you get 7.77 times 10 to the 20th molecules. Right. Now, iridium is very expensive, so we don't typically make a whole gram of this, but if you did, that's how many molecules of that compound would be in there. All right, so same exact conversions we saw last time. We're just using the molar mass for the compound in place of the atomic mass as we did for elements when we first introduced this. All right, so that's pretty much a review, just taking it one step further to talk about compounds instead of elements. But now we're going to see some other ways that we can use molar relationships. And what we're going to start doing now is relating the mass percent of a compound to its molecular formula using molar mass and other concepts related to moles. So we introduced mass percent very early on in this course, and we saw that many of the early scientists that were studying chemical compounds, one of the easiest things to do, and one of the first things they did was they measured the masses of the individual elements in that compound, and that's given by the mass percent. So just to review what that is, every compound is made up of two or more elements, and the mass percent for a given element is the mass of that element divided by the mass of the compound Now keep in mind that this ratio here is what we call the mass fraction, but if we want mass percent, we always have to multiply it by 100. Okay, so that's the definition of mass percent, which we learned very early on. And if we now have the molecular formula for a compound, we can use the molecular formula and the atomic and molecular masses to determine the mass percent of any element in that compound. So if we want to use the molecular formula to find the mass percent, we can assume that we have 1 mole of compound. Remember that mass percent is an intrinsic quantity, which means that no matter how much of the compound you have, whether it's 1 microgram or 1 megagram, or however much you have, the mass percent is the same. So if we assume that we have 1 mole of compound, we can calculate the mass percent by using the molar masses. So we take the mass of the element A that we're interested in, that's in 1 mole of that compound, and we divide that by the molar mass of the compound. And then if we want to get percent, we multiply by 100. All right, so basically what we're doing here is we know that when we calculate the molar mass of a compound, we're adding up all of the contributions from the individual elements in that compound, and then to find the mass percent, we can take the contribution from one of those elements that's in the compound, divided by the total molar mass of the compound, and multiply by 100. So with the chemical formula and with the individual atomic masses, we can always find the mass percent for any compound using its chemical formula. All right, so as an example of this, let's look at, again, going back to glycine, the one we did at the beginning where we calculated the molar mass. What's the mass percent of carbon in this compound? All right, so as I said before, if we want to use the chemical formula to determine mass percent, we assume that we have 1 mole of compound. And the mass of 1 mole, of course, would be calculated in one of the first slides here, was 75.07. And then when we calculated this molar mass of 75.07, we remember that the contribution from carbon comes from the number of moles of carbon that are in the formula times the atomic mass of carbon. So the mass of carbon in this 1 mole, we have 2 moles of carbon because of the subscript 2 here in the chemical formula, and the atomic mass of carbon, the mass per 1 mole of carbon is 12.01. That's from the periodic table. So out of those 75.07 grams that are in 1 mole, that represent 1 mole of that compound, 24.02 is going to be made up of carbon. All right, so again, that's just the contribution of carbon to the total molar mass as we calculated it much earlier here. So then if we want mass percent for carbon, we take that contribution from carbon, 24.02 grams, divided by the molar mass of the compound, mass of 1 mole, which is 75.07, and then multiply by 100. And so that comes out to 32.00%. All right, so in principle, we could do this for any element in the formula, and if we did all of them individually and added them up, they should sum to be 100%, of course. All right, so that's how we can now use the chemical formula to get the mass percent. When we first introduced mass percent, we were sort of, taking the very, the early chemistry approach of, well, we don't know anything about, moles or chemical formulas or anything like that. Let's just look at the individual masses of the elements and calculate mass percents. But now if we have the chemical formula, which is really related to the number of moles of each element, we can convert those into masses using the molar masses and then divide them to get mass percents. Okay, so really it's just combining two concepts that we've learned earlier in the course and then one that we learned today dealing with molar mass. Okay, so any questions on that before I move on? All right, so as you can see, if we can go in this direction, if we can use the chemical formula to determine the mass percent, we should be able to work backwards and use the mass percent to determine the chemical formula. So now we're going to see how to do that, but the important point here is that the mass percent is not going to necessarily give you the molecular formula. All right, so if we're talking about covalent compounds, remember that the molecular formula is the total number of each atom in the formula. And so when we introduced this, we saw, for nomenclature that you could have, N2O4, you could have N3O6, NO2. All those are different compounds, and they have different molecular formulas. So if we're using the mass percent, though, all the mass percent gives us is what's called the empirical formula. So let's first introduce what empirical formula is. So the molecular formula is going to tell us the total number of each atom in a molecule of a compound. Or it can be interpreted in terms of moles, as we saw. So when we have the molecular formula of glycine is C2H5NO2, that means you could either interpret it as there are 2 atoms of carbon, 5 atoms of hydrogen, 1 atom of nitrogen, and 2 atoms of oxygen in 1 molecule of glycine, or you could interpret it as there are 2 moles of carbon, 5 moles of hydrogen, 1 mole of nitrogen, 2 moles of oxygen in 1 mole of glycine. So the chemical formula, the molecular formula can be interpreted in terms of either moles or individual atoms, but it's the total number of each atom in that chemical formula. Now the empirical formula is a little bit different. It's the lowest whole number ratio. Now for glycine, the example we've been working through, that's the empirical formula is the molecular formula. But in some cases we can reduce the molecular formula to a lower ratio, and that lowest whole number ratio of atoms in a compound is what we call the empirical formula. Now when we find the formula for ionic compounds, we should realize that we already do this, right? When we find the formula for ionic compounds by balancing the charges, as we learned earlier, you always take the lowest whole number ratio. So, we saw that for calcium and oxygen, it wouldn't be Ca2O2, it would be CaO. You always take the lowest ratio. So for an ionic compound, you don't really have to do anything, or really the formula that you report for the ionic compound is the empirical formula. And the reason for this, as we'll learn later on in the course, is that ionic compounds don't consist of discrete molecules. They consist of those formula units repeating over and over again throughout the entire structure. So we just report the lowest whole number ratio of elements for an ionic compound. But for molecular compounds, we often have differences in the molecular formula and the empirical formula, where the molecular formula, again, tells us the exact precise composition of that molecule, but the empirical formula is just the lowest whole number ratio of those elements. So if we have N2H4, which is called hydrazine, we recognize that both of these subscripts are divisible by 2. So if we take that whole formula and divide it by 2, the molecular formula, we can get an empirical formula that's NH2. Okay? So NH2 would be the empirical formula for the N2H4 molecular formula. If we have H2O, is there any way we can write the ratio as a lower set of numbers? No. So if one of these is already 1, like oxygen is in H2O, we can't do anything to that. So the empirical formula for water is the same as this molecular formula. In some cases, that's going to be true. But then for these other ones, if we have C6H6, both of those are 6, so we can divide them by 6, and the empirical formula for C6H6 is CH. We talked about C6H6 at the end of chapter 4. It's that benzene structure, that hexagon of carbon atoms. That's the actual structure of the molecule, but the empirical formula is just 1 carbon to 1 hydrogen, or CH. And then if we have this more complicated one, B3N3H6, we could divide all of those by 3 to still get whole numbers, and so the empirical formula would be BnH2. All right, so in other words, if you want to convert the molecular formula into the empirical formula, you divide by the greatest common factor. Now, it turns out that empirical formula is not as useful of a quantity, or not as useful of a parameter as molecular formula, because it doesn't tell us about anything about the structure of the molecule. So why do we even care about it? Well, the reason is that a mass percent will only tell you the empirical formula. It won't tell you directly the molecular formula. So in other words, if we have two different compounds that both have the empirical formula CH, in fact there are many compounds that have the same empirical formula CH, all of those compounds will have the same mass percents. We cannot distinguish them based on mass percent alone. So what we're going to start learning how to do is how to convert mass percent into an empirical formula, but when we do that we're only going to get the empirical formula. We have to take another step then to get the molecular formula. Okay? So that's why we have to introduce this now and why it's important for what we're going to be doing from here. So if we want to determine the empirical formula from the masses of elements in a compound or from the mass percents, there's three steps to doing that. So the first thing is we have the mass of each element. So whether it's a mass percent or just the absolute mass of those elements that are in that compound, we have to convert each mass to moles. So empirical and molecular formulas are related to moles, so we have to convert the mass to moles first. So we're going to give you, in many of these problems, certain list of elements, how much grams of each element is in the compound, and we have to convert each of those to moles. And of course, the way we do that is we use the atomic mass of each element to convert it from grams into moles. Alright, so now once we have moles of each element, those ratio of moles is going to give us then the empirical formula. So we have to convert it then to the lowest ratio, because we're not often going to get whole numbers at this stage. We have to convert it to the lowest whole number ratio by dividing each molar quantity. So we're going to take each molar quantity and divide it by the smallest one. Alright, because as we saw, empirical formulas are always reported as whole numbers. There are never going to be any fractions or decimals in an empirical formula. So if we want to convert these molar ratios, which are most often not going to be whole numbers, into whole numbers, we divide them all by the smallest one. That sets one of them to 1, and the rest of them are going to then be relative to that one. Now, sometimes there's a necessary third step, so you're not always going to do this third step. And that's to multiply the empirical formula that you find by a small whole number. To remove any fractions or decimals that you have in your formula. Alright, the biggest mistake that people make when they're doing these types of problems, if you want to know what it is, the biggest mistake they make is they do too much rounding. So as an example, they would get, if they got the formula C 0.5H. So let's say they do the first two steps here, and they get a ratio of 0.5 to 1, which sometimes can happen. You can get decimals there. They'll just round it and say, oh, the empirical formula is CH, round 0.5 up to 1. But in these types of problems, you never want to do that much rounding. Only if it's very close to a whole number, within, like, let's say 0.05 or so, would you actually want to round it up. So this is pretty far away from 1. So if we want to convert this to a whole number ratio, what we want to do is multiply this by some factor that's going to remove that decimal. So if you have 0.5 and you multiply it and you double the whole thing, you're going to get rid of that. So we double the whole thing, and the correct way to report this empirical formula would be CH2. Or as another example, let's say you get N1.333H. Let's say that's what you get as your empirical formula. Well, again, a common mistake to make would be to round this. To say, oh, 1.333, that's pretty much 1, let's call it NH. But you don't want to do that much rounding in an empirical formula problem, because what you can do is multiply this by a whole number. Again, this time it'd be 3 to get rid of the 0.333, and you get N4H3. Okay? So you don't want to do too much rounding. It's tempting to just write this as NH, but really the correct way to do this would be N4H3. So only if the number is really close to a whole number are you going to round it to that nearest whole number. If it's 0.25 or 0.75, you want to multiply it by 4. If it's 0.5, you want to double it. If it's 0.333 or 0.666, you multiply it by 3 to convert it to a whole number. Okay, so don't do too much rounding in these. I don't know if that's going to come up in any of the examples we do today, but you certainly could see it on some of the homework problems. Alright, so let's do some examples of this. Alright, so if we have this compound here, vanadilyl chloride, it's a metal compound with vanadium, and it's actually a liquid at room temperature, so kind of rare. And a sample of this compound is found to consist of 1.47 grams of vanadium, 0.462 grams of oxygen, and 3.07 grams of chlorine. What is the empirical formula? Alright, so again, this is an example where I'm giving you absolute masses of all the elements that make up that compound, and we want to convert that into an empirical formula. So the first thing we always have to do in these types of problems is convert all of the masses into moles. So for each element, we're going to find the number of moles. So for vanadium, there's 1.47 grams. And then we want to convert into moles, so we have to divide by the molar mass, or the atomic mass, for vanadium, which is here on the periodic table, 50.94. Okay, so we divide by the atomic mass to convert masses into moles. And so that means this sample of compound has 0.02888 moles of vanadium. Alright. We do the same thing for the other elements. Moles of oxygen, we have 0.462 grams. 1 mole of oxygen has a mass of 16 from the periodic table. So grams cancel, we convert into moles, and we get again about the same amount, 0.0289 in this case, if we're being careful with our rounding. And then finally for chlorine, the moles of chlorine, we have 3.07 grams of chlorine. From the periodic table, the atomic mass of chlorine is 35.45, so we divide by that to get the number of moles. So we have 0.0866 moles of chlorine. Alright, so this is the number of moles of each element in this sample of compound. So we can just write an empirical formula with those. But remember that empirical formulas are going to be conventionally reported with whole numbers. So if we write the formula as V 0.0288, O 0.0289, CL 0.0866, that's obviously not a correct way to report an empirical formula, which would be in whole numbers. So the way that we convert these to whole numbers is we divide all of them by whichever one is the smallest. So the smallest one is vanadium, which is 0.0288. So we divide all of these coefficients, all these subscripts by 0.0288. And when we do that, we get 1 vanadium, because that divides to 1. For oxygen, 0.0289 divided by 0.0288, that would come out to something like 1.001. That's pretty close to 1, so we'll call it 1. We don't have to round that. We don't have to do anything to that. We can round that. And then finally, CL, 0.0866 divided by 0.0288 is exactly 3, so we get VOCl3. Alright, so we're just taking these molar amounts and converting them to whole numbers by dividing them. And in this case, we can stop here because we don't have any fractions or decimals left. We can just report that as the empirical formula and we're done. And so that is the empirical formula of this compound. Alright, so that's where we take the absolute masses, convert them into moles, and get the molecular formula, or the empirical formula. Now we can do a very similar thing if we have mass percent. So let's look at this example here. We have a binary compound consisting of boron and fluorine, and it's 15.94% boron by mass. And we want to know what's its empirical formula. Alright, so keep in mind a couple keywords here. Binary means it only has 2 elements, and we're telling you that those 2 elements are boron and fluorine. And we're giving you the mass percent of one of them, which is boron. So if we want the mass percent of the other one, we have to subtract it from 100. So if we want the mass percent of fluorine first, so if we have the mass percent for every element in the compound, we can also use that to get us into an empirical formula as well. And that's what we're going to do in this example. So for fluorine, we have 100% minus that 15.94. So fluorine, the mass percent is 84.06. All right, there's only 2 elements, so if it's 15.94% boron, the rest has to be fluorine. Okay, so those are the mass percents, and then how do we deal with mass percents when we want to convert those into an empirical formula? So as I said, when you're doing these types of problems, you can assume whatever amount of compound is convenient for you. So if we're dealing with mass percents, let's assume that we have 100 grams of compound, and that would tell us then that we have 15.94 grams of boron and 84.06 grams of fluorine. So anytime we're dealing with mass percent, it's convenient to assume 100 grams of that compound. And then those percentages that we have just become mass amounts, which we can then convert into moles just like we did before. So if we assume 100 grams of compound, the moles of boron, we have 15.94 grams. The percentage is converted into grams. We're talking about 100 grams. And so 15.94 grams of boron, and then we're doing the exact same step we did the last time, converting into moles by using the atomic mass. So the atomic mass for boron is 10.81. And so this 100 grams of compound that we've assumed is going to have 1.474 moles of boron. Now, I should point out, we can assume whatever amount of compound we want, but for mass percent, 100 is the most convenient, so that's what we're doing here. For fluorine, we have 84.06%, so that converts into 84.06 grams if we're assuming 100 grams of compound. And the atomic mass of fluorine is 19. And so that gives us 4.424 moles of fluorine. All right, so those are the molar amounts of each element in this binary compound, and then the ratio of those two, the lowest ratio is going to be the empirical formula. So B 1.474, F 4.424. That technically is the empirical formula, but it's not the standard way of writing it in whole numbers, so you have to divide both of those by the smaller one, which is 1.474. And again, these come out pretty nicely to whole numbers, and it comes out to BF3. Alright? So very similar to the last one, it's just when we have mass percents, we assume 100 grams of compound, and we use those percentages as the masses that we're starting with. Now, as I said, though, this only gives us the empirical formula, so what if we need the molecular formula? You need another piece of the puzzle, and the other piece that you need is the molecular mass. So if we can use the mass percents or the mass amounts to find the empirical formula, if we also know the molecular mass, we can then find what the molecular formula is as well. And the relationship that's key here is that if you take the empirical mass, which is the mass, the molar mass of the empirical formula, that's going to be related to the molecular mass by some whole number multiple, because the empirical formula is some whole number multiple of the molecular formula, some whole number divisor, I guess. So we're going to, in many of these problems, we'll give you the molecular mass, or we'll give you the information you need to find it, not the molecular formula, of course, but we'll give you some other way of finding the molecular mass. And then with that molecular mass, in concert with the empirical formula, you can figure out what the actual molecular formula is. So as an example of this, let's say we have a molecule whose empirical formula is CH2. So there are tons of compounds with the empirical formula CH2. And its molar mass or molecular mass is 70 AMU, or 70 grams per mole, however you want to think about that. So if we have the empirical formula and the molecular mass, how do we find the molecular formula? So for CH2, we first need to find the empirical mass. That's just the molar mass for the empirical formula. So CH2 has one carbon, which is 12.01. I guess we'll do it in AMU. So remember that AMUs and grams per moles are kind of interchangeable in these types of problems. So, but we could use either one. So that's one carbon and two hydrogens. So the empirical mass is going to be given by this, which is going to be rounding to a whole number, 14 AMU. I gave you the molecular formula in a whole number, so we don't need to really go any more precise than that. So the empirical mass is 14 AMU. And so if we divide the molecular mass by the empirical mass, that's going to give us the whole number that relates the two. There should be a whole number if we did this correctly. So the molecular mass is given to us as 70 AMU. The empirical mass that we just calculated is 14. And so that means they're related by the number 5. And so if we want to convert this empirical formula of CH2 into a molecular formula, all we have to do is multiply it by 5. So we take that empirical formula CH2, multiply the whole thing by 5, and our molecular formula in this case would be C5H10. Alright, so once you have the molecular mass in concert with the empirical formula, you can find out what it is. Alright, so we'll do one last example here that sort of puts it all together. So we're going to give you, both pieces of information. The information to find the molecular formula, the empirical formula. We're going to give you the molar mass and ask you to find the molecular formula. So this is just combining those last two steps. So let's say we have a compound that is 28.18 mass percent manganese, 30.80% carbon, and 41.03% oxygen. And we know that the molar mass is 389.98 grams per mole. So what is the molecular formula? All right, so again, the two steps are first find the empirical formula and then find the relationship between the empirical formula and the molecular formula by using the given molecular mass. So if we're given mass percents, the way that we can find the empirical formula, again, is to assume 100 grams. So we convert each of those percentages into a molar amount. So if we assume 100 grams of compound, that means we have 28.18 grams of manganese. The atomic mass of manganese from the periodic table is 54.94. So this very familiar step that we have of converting mass into moles, we divide by the atomic mass, and so we have 0.05129 moles of manganese. Sometimes it's good in these problems to keep at least a few decimal places, 3 or 4, so you don't do any rounding errors. It's going to cause heart rate later on. So let's try to keep 4 significant figures when we're doing this, since that's what we're given. The moles for carbon, we have 30.80%, so we assume in 100 grams, that means there's 30.80 grams of carbon. 1 mole of carbon has an atomic mass of 12.01. So that means we have 2.564 moles of carbon. And then finally for oxygen, the last percentage is 41.03. So 41.03 grams of oxygen. 1 mole of oxygen has a mass of 16.00. And that gets us to the same amount, 2.564 moles of oxygen. Alright, so with this information, we can now finish the empirical formula. So the empirical formula is going to be Mn 0.5129, carbon 2.564, oxygen 2.564. Those molar amounts become the subscripts, and then we divide by the smallest one. 5129 is the smallest, we divide all of them by that. And so the empirical formula for this compound is MnC5O5. Alright, so this divides by itself to give 1, and then we have these two divide to give 5, so we get MnC5O5. So same exact set of steps, converting mass percents into moles. That gives us the empirical formula, but we can't stop here, so we have to determine the molecular formula of this compound, and that's where we need the molecular mass. So I'm going to insert one page and we'll finish this up. Alright, so the last step then is to find the relationship between the molecular mass and the empirical mass. Alright, so the molecular mass is given to us in the problem as 389.98. And then the empirical mass we have to find. So the empirical mass, again, is the mass of the empirical formula. So our empirical formula is MnC5O5. So it's going to be the mass of manganese plus 5 times the mass of carbon Alright, so it's going to be manganese plus 5 times carbon plus 5 times oxygen gives us somewhere around 195. So the empirical mass is 195, so when we divide the two, molar mass divided by empirical mass, we get 2, a factor of 2. And so that means our molecular formula is going to be 2 times the empirical formula. So when the ratio of the masses is 2, that means the ratio of the molecular formula of the empirical formula is also 2. So if we take our empirical formula, MnC5O5, and we double it, that's going to give us the correct molecular formula, which is Mn2C10O10. Alright, so those are sort of the concepts we're going to deal with today. So next time we'll see a slightly more complicated example of going from masses into empirical formulas, and then we'll move on to some new things after that. We don't reduce it. So remember, the empirical formula is the reduced form. For a molecular formula, you don't want to reduce it. You have to report all the numbers as they are. So no reducing in this case.